This is the openRow system. It is a rowing telemetry system, meaning it tracks a number of important metrics while rowing that the user can then analyze to become a better athlete and improve their technique. openRow tracks acceleration data with a built-in accelerometer and force using a custom load cell integrated oar lock. Here's a quick demo on how the device works. First is powered on with an internal switch. Then the device plays the loading screen. In this case, it is on data mode. So when the device receives data, it shows on the screen for the user to read. By flipping another internal switch and resetting the device, it goes back to the loading screen and is now on force curve mode, where it plots force over time on a graph for the user to see. After a period of inactivity, the screen refreshes. A feature of the openRow system is its online web page, where you can view the data live through Bluetooth Low Energy from the device to your computer or cell phone. Here's a quick demo of how the website and the device interact with each other. First, the openRow Bluetooth device is selected in the menu. Once connected, the user can now view strokes per minute, acceleration in meters per second squared, force, uptime, as well as an acceleration over time graph and a force over time graph. So how does it all work? Let's start with the device. First of all, the MCU here is an ESP32. All the tasks are run on Core 1. The accelerometer is an MPU 6050 and communicates with the MCU over I2C. The load cell amp connects to the load cell oar lock and then is communicating with the MCU also over I2C. The whole thing is powered by a 3.7 volt, 2000 milliamp lithium polymer battery, which is charged and managed by a TP4056 battery control module. The LCD display, which communicates over SPI, is a RGB 240 by 320 pixel display. Lastly, the ESP32's built-in Bluetooth Low Energy capability and PCB antenna communicate with a nearby phone or laptop running the openRow live dashboard. For an in-depth dive on how the Bluetooth Low Energy communication works, check this project's design engineering report. Now for the custom oar lock. The oar lock is made out of flexible nylon material and is 3D printed that way. The bushing pulls off and the gate is open so you can put the oar inside. Once closed, it goes onto the pin just as a Concept 2 oar lock would usually, using Concept 2 bushings. The oar lock is designed to row and have critical measurements exactly like the Concept 2 oar lock. However, inside is an integrated button load cell. A button load cell is a small strain gauge inside of a sealed piece of button-like metal. This was chosen for its durability, water resistance, and compact form factor. When using the website, you can save the data recorded for later analysis. In this example, take a few strokes, disconnect from the device, click Export CSV file, open Google Sheets or another similar platform, click Import, and choose your file. Once uploaded, don't change anything, click Import Data. Then you see all your data in the table there. You can click two axes for a graph, click Insert, Chart, and change it to line. Now you have a force curve throughout your entire row. Lastly, here's a brief teardown of the device itself. 4 screws hold the case together, and those 2 just hold the screen in place. After undoing the 4 screws, we can take the top half and the bottom half apart. Here the battery is unplugged. This is the battery unit. It is the lithium polymer battery and the battery control module. Next, we can pop out the display and the rest of the device. Part of the display is covered up with electrical tape to prevent short circuits. This is the rest of the device. This part is the NAU7802, which is the load cell amplifier and ADC. This is the ESP32 with its built-in PCB antenna. And the blue part is the MPU 6050, which is the accelerometer that this device uses. On the back, you can see how it's all connected. If you'd like to learn more about this project, every single detail is explained in depth in the design engineering report below. Unfortunately, this project has yet to be tested in real rowing on water. However, over the coming months, I'll be designing a JavaScript system that analyzes the data received over Bluetooth from this system, and a physics project that goes in depth into the biomechanics of rowing using some of this data. And lastly, as Lake Ontario's water gets warmer and the risk of a failed oar lock becomes a little bit less dangerous, I'll be testing this oar lock on water and eventually a sculling system with 2 oar locks. Thank you for watching, and I hope you have a great rest of your day.